We're talking about glaciers and the hydrological cycle and the fact that glaciers are an integral part of that hydrological cycle. The point I'm going to make being that the characteristics of glaciers to some extent derive from their position in that cycle. Now at this stage I'm sure you all already know a little bit about the hydrological cycle, so I'm not going to go into that in detail, and you will understand my simple cartoon wherein we have the oceans, seafloor, the land surface, the atmosphere. And we have evaporation from the oceans and from the land, we have moisture in the atmosphere, and we have precipitation of that moisture back into the oceans and onto the land. That precipitation might be precipitation in the form of rain, or precipitation in the form of snow. That precipitation, that water, then makes its way back into the ocean by overland flow or groundwater flow, etc. You're familiar with that. Now what I'd like you to think about is what happens particularly when we do have a lot of snowfall rather than just a lot of rain, and particularly in climatic conditions where a winter's snowfall does not melt through the following summer. So gradually we start to build up settled snow on the land surface. Well, as we'll talk about later on, that's how glaciers form. In the context of the hydrological cycle, what that means is that sometimes there is a fairly rapid turnaround through this hydrological cycle with evaporation, precipitation, flow primarily through rivers back to the oceans, and in that situation the return flow takes typically a couple of weeks. Your average raindrop, if you like, if it falls into a river anywhere in the world, on average takes about 2 weeks to get back into the ocean. By contrast, once we start building up ice sheets on the land, well then, if precipitation falls as a snowflake, then on average, if it's following a glacial pathway, we're talking more like 10,000 years as being the average length of time it takes for that cycle to be completed. So glaciers and ice sheets are storage points in the hydrological cycle that hold up that return flow back to the oceans. As a storage point, there's a volume of ice in there which is water that hasn't been returned to the oceans. So as ice sheets grow, sea level falls. When ice sheets melt, that water is returned to the oceans and sea level rises. Now a lot of you will already have heard from me on the topic of glacial isostasy, glacial eustasy, hydroisostasy, and the complications that intervene between the simple pouring of water into the oceans and the resulting sea level, but you'll see at least here that there is a very direct connection between climate, the existence of glaciers and ice sheets, and how much of the Earth's water is held in ice sheets rather than being held in the Earth's oceans. And as I suggested before, you can very quickly read up in the literature what kinds of percentages we're talking about here. But just to give you a rough indication of the order of magnitude that we're talking about, during maximum glaciation, the maximum of the last glaciation, about 197 metres equivalent sea level, so nearly 200 metres worth of global sea level, was locked up in the big ice sheets on the Earth's surface. At the moment, there's about 60 or 65 sea level metres locked up in the ice sheets. So there's still a lot of water, important point, there's a lot of water locked up in the ice sheets even now. But there was much more during the last ice age. So there was an awful lot of water, about 132 metres sea level equivalent, that was released from glaciers at the end of the last ice age. And that release of water had a major impact on Earth's surface systems and on the hydrology. So glaciers are an important part of the hydrological cycle, and they're partly affected by it, as we'll see in a minute when we talk about the characteristics of snowfall landing on glaciers and creating glaciers, but also glaciers impact the hydrological cycle through this storage delay mechanism.